welcome to this pencast on the Mealy coffee machine implementation in Verilog. My name is Kevin Lamas, and I will run you through this pragmatic approach towards writing the implementation. First of all, when you go to OnCourse, you will see the state diagram. And the state transition diagram will show you all the states and all the transitions that happen in the system. Please note that the most important bits of information are always on the right side, on the middle of the arrows. So it might get tricky, especially with a lot more states, but it always follows the same convention. In order to start and apply some basic structure to our code, we will look at the inputs of the system, which is on the left side, the Mealy machine itself, the module, and we have an output coffee. These are all denoted here in the code, and as you can see, the coins are 2 bits wide. Furthermore, you can call your states names, or you can use decimal numbers. It doesn't really matter as long as you know what you're doing. I personally like to use local parameters, so you can use for example, this decimal notation for your states, but it's up to you what you do. Furthermore, I make some additional registers. One of the 2 bits wide registers are the states, because we have 3 states, and 3 states in decimal is, so if you count, you have state 0, 0, 0, 1, and 1, 0. So you need 2 bits for this. And coffee next is going to be your output, which is determined inside the always star block, which I'll also show in a bit. Furthermore, what is important to know is blocking and non-blocking. All details aside, you always use the equal sign in an always star block, and you will use this sign here, a smaller than or equal sign, when you're in an always postage clock block. This clock block is also the next thing you need to implement, because we cannot change our states during an always star block. We have to do this in a clocked block. And this clock block is, because it's on the postage, we need to use this sign, and we need to assign our next state, and every time the reset is, for example, 0, because if the reset is 0, our next state is going to be put in our current state. However, if we press reset, then it will go to the else statement here, and you'll see that it will send back the first state, namely send 0, when there's no coins in the system. Well, so far this is the structure. This part I have now explained, and the last part is something that you could possibly try to copy and try to fill in yourself. However, if this is too hard, I will explain everything else from now on as well. So we have this structure here on the bottom. This is our always star block, and as you can see, I've added some basic statements already. One of the first statements is, if you reset, your next state should be 0, and your coffee output should be 0. If that's not the case, then we are going to look through the state transition diagram. So the state transition diagram, as you can see here, I'm missing the reset line. Please have it in there, or else the code will possibly malfunction. However, if we have this case switch, you can see that if you're at send 0, that's the first state, the only logical steps towards, for example, send 5 is towards going to B10, which has an output of coffee 0. How do we implement this? Okay, we implement this by looking for each state individually, and then working our way from top to bottom. That's what I would suggest. Furthermore, I already added some default values here. Technically speaking, you don't need these, because if you implement everything correctly, it will not go towards the default states, because everything is already defined. So first of all, we start with send 0. So we have to look from the perspective of this state. And as you can see, there is a transition available from send 0 to itself. How can you achieve this? By inserting 0 coins. Okay, if coins is 0, output is 0, output is 0, and the state stays 0 as well. Send 0. There you go. If you add coins B10, then you will get to send 5. And if you see here, if you look at this line, you see B10, and the next state is send 5. And the output will be 0. So from there on, you can basically follow all the lines and do this for every state. Now I can show an example here as well. For example, if we are at send 5, so we have to look at this state, you see that there's a transition from send 5 to send 5. It needs input 0. Input 0 happens here, and it has output 0 and output 0. And our next state, from that state on, will be our own state, which is called send 5. And from there on, you work your way towards send 10. And then the only thing you need to do is assign an output. This output is assigned by the following statement. And because you define your coffee next inside the always star block, you can just basically connect it as a wire to the coffee, which then will be checked in the grading software. So this is the full structure of the code. Please pause the video if you need the structure. And if you don't need it, then that's all good. And I will give you some tips on debugging, because this screen looks very daunting, but look at this part here. It will show that the BMC has failed. And a BMC failed means you probably have to look at the debug window. And if you look at the debug window, on the left side, you can see dot and ref. The grading software will actually look at your output, because it doesn't matter how you implement your software as long as this output is correct. And it will check for every available input combination. As you can see, I made sure there was a version of my code that was incorrect. That will result in one version, which is the dot, which is your device under test, which is your own code, and the reference not being the same. If that's the case, then the software will actually not pass your code, which would be sad, of course. So please use this wave window, because this is where you will be debugging from most of the time.